Now that we introduce the concept of the electric force, we move to introduce the concept of the electric field. Electric field is simply related to the electric force. So we talked about the electric force, said we have two charges, Q1 or Q2. Here we call them capital Q and small q. In order to be able to measure the electric field at one point, we simply pick a very tiny charge Q and put it at that point and then try to measure the force affecting that charge. So by definition, the electric field is the force affecting an infinitesimal charge per the value of that charge. So by definition, you find the force affecting that charge and then you divide by the value of that charge, and then you take the limit as you make this charge small enough. Why do we make it small enough? Because when you put this test charge, we don't want it to affect the other distribution of charges all around it, because remember there are forces. These charges try to attract and repel against one another. So if you're going to put a tested charge at one point and you want to measure the force in that charge, you better make that charge extremely small. So the force it's affecting with which it's affecting other charges is going to be small. So this is the definition of the electric field, is really the force affecting an infinitesimal charge per that charge. So you divide that force by the value of the charge, and then you try to make this one as small as possible. I know when you see the word limit, we get a little bit worried, but limit here means make it as small as possible in order not to disturb the other charges around. Another way of looking at it is to calculate the force when this charge Q is one column, because when you make it one column, its its magnitude and the expression of force disappears. So you can look at it from both sides, but I would say the more accurate one is to consider an infinitesimal charge. So the electric field is nothing but the force per charge, the force affecting an infinitesimal charge at that point, and then you divide it by the value of that charge. So the stronger the value of the electric field means the stronger the force affecting an infinitesimal charge to be put at that point. Okay, so the electric field is nothing but a force. If you go back to the expression we derived before for the force, it was Q1, Q2 divided over 4 by epsilon r cubed, and then you multiply by the vector. It's exactly equivalent to Q1, Q2 over 4 by epsilon divided by the distance r squared, and then you make this one a unit vector. Unit vector means it is a vector divided by its magnitude. This is why this one becomes r squared, not r cubed. These are exactly equivalent. So what we did here, we said we replaced the other charge Q2 by 1. This is what I told you. It's another way of calculating the electric field. Or we made it as a small charge Q here, and then after we calculated this expression, we divided the whole thing by Q. So Q will disappear, and then you end up with only 4 over 4 by epsilon r squared. Then the electric field resulting from a positive charge, if you have a positive charge, say it's at the center, at the origin, then it creates an electric field everywhere around in the space, and this is the value of this electric field. This electric field represents the force that will affect a point charge put at any point, okay? And then if you normalize it by the value of that charge. So you take a small q and then divide by q. So you can see the electric field is pointing outward. Why it's pointing outward? Because if you put a positive charge here, maybe I should try to draw it for you. If you put a positive charge here, then these two charges, this charge at the center is trying to push this charge away from it. This is why the electric field is going to be pointing this way. It's in the outward direction. The same thing will happen if you put a charge here. If you put charge at this point, then this charge at the center is trying to push this charge in the outward direction. Then the direction of that field will be in that direction here. So you can see it's pointing in the radial direction, and this radial direction in spherical coordinates is what we call AR. So this is the electric field resulting from a point charge. What if we have any distribution of charges? Then we apply superposition. We say that the field at any point in space is the sum of the field resulting from all charges in the space. Of course, very far away charges contribute negligible field. Let's take a look at an example just to help us understand this concept. We have here a charge of value minus 1 microcoulomb. So here the charge 1 microcoulomb is located at the origin. So it's located at the point 0, 0, 0. I would like to know the electric field created by that charge at the point 1, 1, and 1. And as I explained, the electric field at the point 1, 1, and 1 represents the force affecting a test charge that's put at that point. Bear the value of that test charge. So you normalize it after you calculate the force. And we make a small charge so as to avoid disturbing that original charge that we have here. We go to the expression. It is Q over 4 by epsilon r squared. R squared is the distance between the location of that charge and the point at which we are calculating the field. And then it's going to be in the AR direction, in the radial direction. So this is a direct substitution. This is the expression. It's Q over 4 by epsilon. And here I'm sorry I missed the r squared. There should be an r squared here in the denominator. Okay. So if you calculate this expression here, the position vector at the point while calculating the field is 1, 1, and 1. So if you want to calculate the unit vector pointing from the origin to this point here, say the point is here, so I can simply pick that point here and call this point the point 1, 1, and 1. Okay. Then in that case, this is my R. This is the vector pointing from the charge to the observation point, the point where I'm measuring the field. And the unit vector in this direction is AR. So what you do, you calculate this expression. It is you put your charge value. It is minus 1 microcoulomb as we mentioned. 1 over 4 by epsilon is equal to 9 to the power 9. And of course here I forgot to divide by r squared. Then you have to divide by the length of this vector, which is square root of 3. So this whole expression here, you can simply divide it by 3, which is square root of 3 squared. And then you multiply by the unit vector that you have. This is the unit vector. It is the original vector divided by its magnitude. So you can see square root of 3 and you have 3. So this will give you a square root 3 to the power 3. This is what we had originally in the force expression. You calculate this expression and then you have the direction of the force. And you can see this force is an attraction force. It's not pointing outward in the direction 1, 1, and 1. It's actually trying to attract this charge to the origin because there is a negative sign here. Because if you put a negative charge at the origin and they put a positive charge at this point, then effectively they are trying to attract one another, so this charge is being pulled in that direction. This explains this negative component here. So if you go ahead and simplify this expression, you will see that the answer that you will get is this number here divided by 3. I was forgetting to add the r squared, so I divided now by 3. And this is multiplied by the vector 1, 1, and 1, ax plus ay plus az. So this gives you exactly the force, the electric field, which is nothing but the force affecting a tiny electric charge which was put at the point 1, 1, and 1, and then you divide by the value of that charge. So it's force per charge. So this is the value of this electric field, and you can see when we have stronger charges, then we have stronger electric field. If we have weaker charges, we have weaker electric field. If we are far from the point where the charge is, then r squared becomes bigger, and then the electric field will become weaker. I'm showing you here the electric field lines inside the capacitor. And the capacitor I explained to you earlier, it's really a metal plate here connected to the positive electrode of the battery. And this is the positive plate, connect the positive electrode. This is the negative plate, connect to the negative electrode. So the battery, you can imagine there is a battery here, and this battery looks something like this. It's really the one supplying positive charges on this part. There are positive charges here, and there are negative charges here on this plate, okay? And between them there is an insulator. And you see the electric field lines, they are pointing from the positive charges, negative charges, and they look almost as if they are vertical to the plates. Okay, and in many of our calculations, this is called the parallel plate capacitor, we assume that the field is uniform, meaning that the field is the same everywhere inside this volume. It does not change by position. So it is pointing in this direction. It's pointing normal to the plates from the positive charges, the negative charges, and its value does not change. It is uniform everywhere. Okay, and we usually ignore the field outside, which we call a fringing field. You can see there is another field pointing again from positive charges to the negative charges, but this is outside the capacitor, and this one is usually way weaker than the one inside the capacitor. We call this, the one outside the capacitor, the fringing field. We tend to ignore that very often to simplify the calculations. Of course, we can calculate it using advanced techniques like method of moments or whatever, but for now, for this course, we simply ignore the fringing field. Now we start to link these concepts of electric force, electric field to circuits. How is that related to voltage? How is that related to current? This is what we need in our circuits. So the electric potential, by definition, it is the integration of the electric field. It's the work done by the electric field. So the electric field will try to move a charge from one point to another. This means it's putting work. I know some of you have very good mechanical engineering background and you understand the concept of work very well. So the work done by force is simply F dot dl. So the force that we have here is nothing but the electric field. The definition of the voltage difference between 2 points, VAB, which is VB minus VA, is the integral from A to B of E dot dl. It is simply the work done by the electric field. The unit of the electric field is volt per meter. dl here is a length vector, and it has units of meter. This is volt per meter. You multiply by meter, you get volts. This is the voltage difference between any 2 points. So this is the definition of the voltage difference. This is so when there is a voltage difference between the terminals of a resistor. This simply means is the electric field going through, and this electric field, okay, this electric field is forcing the current to flow in the same direction, the current I, and this what creates this potential difference, because the electric field is moving the charges along this resistor from one side to another, and then it's putting work, and this work is represented by the voltage difference. There is a voltage difference between this terminal and this terminal. Now, one other important concept in electromagnetics we use very often in our work is that the electric field will try to move electrons against its direction and try to move positive charge in its direction. So, for example, if you have an electric field in this direction here, E, if you have an electron, this electron will start to drift against the electric field with a velocity V. And this velocity is related to another property called the mobility of the electron for this type of material. If you have here a positive charge, this positive charge will drift in the same direction of the electric field, creating current. So both of these will create current, okay? So the direction of the current is the same as the direction of the electric field. This is a fundamental concept. And the relationship between the electric field and the current is this one. J is equal to sigma E. J is the current density. Remember, the more electrons you have that are drifting with the electric field, the higher the current per unit area. So this J is really nothing but a current density. It's ampere per meter squared. If you want to get the total current, you have to integrate over the cross section, whatever this cross section is. The term proportionality between the current density and the electric field is called the conductivity. So this term here is called electric conductivity. Conductivity here, this one here. And this conductivity is really another property of the matter. Every type of material, including our bodies, they have their own conductivity. The higher the conductivity, the more electrons available for conduction. The lower the conductivity, the less electrons available for conduction. And so this is very important. So for electrons, for conductors, the conductivity is pretty high. For insulators, conductivity is very low. Okay, so remember this concept here that J is equal to sigma E, and the potential difference is nothing but the work done by the electric field. Because when we start to use circuits, when we start to talk about resistors, capacitors, inductors, we tend to forget that. The voltage difference is the work done by the electric field, and the current is nothing but the electrons drifting by the electric field. An important analogy that I usually ask non-electrical engineering students to remember between the potential difference between 2 points, which result in a current flowing from the higher potential to the lower potential, meaning there is an electric field flowing from the higher potential to the lower potential, meaning that electrons are drifting in the opposite direction. All of this is very similar to waterfalls. For waterfalls from higher elevation to lower elevation. So this means there is a higher potential there is a lower potential here. Okay, and you can see that the lines of the flow of these is really the direction of the current, and this is the same that we have here. So keep this in mind, that there is a big similarity between water flow from higher elevation to lower elevation and current flowing from higher potential to lower potential, or electric field pointing from higher potential to lower potential. Okay, so these are all very similar, and they have essentially the same interpretation. Now let's take a look at one example. We have here a parallel plate capacitor, so you have here a positive electrode and a negative electrode. And this is really a lossy capacitor, meaning that the material inside the capacitor is not a perfect insulator. It has a finite conductivity. The conductivity has units of Siemens per meter, and this one here has conductivity of 10 to the minus 3. Conductivity can be way higher than that, but this is a lossy capacitor. The separation between the two plates 2 millimeters, and the area of each one of these two plates is 1 centimeter squared. We would like to know the electric field inside this capacitor. Of course, the electric field will be pointing from the higher potential to the lower potential, from the 5 volts to the 0 volts. There is a voltage difference here. We would like to know the current J flowing inside the capacitor. Yes, there is a current flowing because this is a lossy capacitor. For an ideal capacitor, you cannot get any electrons flowing. But this one is a lossy one. It has finite conductivity. There are some electrons available for conduction. And we would like to know also the total current flowing in the cross section. So if you simply draw a line here, this is really a plane. Try to know the total current flowing across this plane here, I. So we assume here the field is uniform. Field is uniform meaning that I'm not gonna be worried about the fringing fields pointing from the positive electrons to the negative electrons in the outside. The field is only confined to the inside of the capacitor, and it's pointing from the positive electrode to the negative electrode, and it does not change its position. It's uniform. So this simplifies our life a lot, because we can apply the expression that the voltage difference is simply the work done by the electric field. So I will call this direction pointing downward here as X, and then we'll see how we can solve this problem. So the voltage difference that we have, which is 5 volts, is nothing but E dot dl. And remember, dl is simply the infinitesimal length pointing from the positive electrode to the negative electrode, which is nothing here but dx, because I assume that this direction is x. But because the electric field and dl are in the same direction, I replace this inner product E dot dl by E dx. But the electric field is uniform, then I can take it out from the integral. I integrate from the top electrode to the bottom electrode, then I get the length which is 2 millimeters. So the integral of dx will give you x. You substitute from 0 up to L, from 0 up to 2 millimeters, then you get D, which is D equal 2 millimeters. So this is the expression that we get, that assuming uniform field, 5 volts is equal to ED. So the electric field is nothing but 5 divided by D, which is here 2 millimeters. Then you get a pretty strong electric field, 2500 volts per meter. So this is the magnitude of the electric field. If you want to write it as a vector, it is pointing in the downward direction, which we called it the x direction. Then it's 12500 in the ax direction. It has a unit vector pointing in the x direction. We know then that at every point inside the volume of this lossy capacitor, the current density is equal to sigma E. And remember, the current density J is in ampere per meter squared. Then you multiply, you put your sigma, which is 10 to the minus 3, you multiply by 12,500. You get the J as a magnitude. This number by this number, you get 2.5 ampere per meter squared. If you want to get the total current flowing in the cross section, what you have to do, you have to imagine that you create a plane here that cuts this capacitor, and then you want to determine the total current flowing in this area. We know that in every unit area we have this number here, 2.5 amperes per meter squared. Then in 1 centimeter squared, how much is flowing? Luckily, this is a uniform problem. The current density does not change from one point to another. Then the current is nothing but J dot ds. J is in the same direction as the unit area ds. ds is really nothing but an infinitesimal unit area here. You must be familiar with that from your work and other courses. Then they become J ds. You multiply the 2.5 by the area, which is 1 centimeter squared. Then it's 10 to the minus 4 meter. Then you get 2.5 10 to the minus 4 ampere. This is the current flowing from the top electrode to the bottom electrode. So now we know that if you apply a 5 volts difference, you get a current of 2.5. Actually, it's 0.25 milliamps flowing from the top electrode to the bottom electrode. So this whole structure really behaves like a resistor. It's really a resistor, and in many occasions you forget that there is an electric field inside the resistor, and this electric field is what moves the electrons. This what creates a voltage drop, and this what really causes the electrons to drift and then create the resistor as we know it. So the example I've shown you can be summarized with this one. There is a resistor here. For DC, the capacitor is really a resistor. There is no other current existing other than the conduction current. This value of this current, we agreed, it's 0.25 milliamperes, and the force is 5 volts. So this whole structure is equivalent to a resistance R, which is equal to V over I. We know from Ohm's law that the voltage and the current are related by the resistance. And the resistance is actually related to the conductivity that we talked about earlier, but I'm not going to get into that. So we divide 5 by 0.25 milliamps. You get that the resistance of this capacitor is 20 kilo ohm. This is the resistance it represents to the current. So from now on in this course, I'm not going to be talking about fields anymore. I will show you simply batteries, and these batteries they act really like electron pumps. The bump currents bump electrons in this direction, the bump current in the circuit in this direction, and when the bump currents, they are actually creating electric field everywhere in the circuit. This electric field will carry out a work across each resistor to move electrons from one side to another, creating the voltage drop. But I'm not going to be mentioning this anymore, but it has to be implicit. You have to understand it, that there is electric field everywhere in the circuit. It is the one that's causing electrons to drift. It is the one that's creating the voltage drop, because the voltage drop is nothing but the work done by the electric field. So from now on, I will only focus on circuit analysis, but you must keep this other aspect of interpretation of the function of the electric circuit in the background.